Hey, so welcome everyone. We're very happy to have Andrew Stuart this week. So Andrew Stuart is the Bren Professor of Computing and Mathematical Sciences at Caltech. He was previously a professor at Warwick and before that faculty at Stanford and Bath. Did his PhD in Oxford and postdocs in Oxford and MIT. So Andrew's won a lot of awards. I've got sort of, several listed here. So he won the Leslie Fox Prize for Numerical Analysis, the Siam James Wilkerson Prize, the Whitehead Prize, and I think at least 3 or 4 other prizes. So it's a very celebrated mathematician. We're very happy to have you here. So Andrew is going to be talking about learning linear operators, and I believe you have 2 of your collaborators on this project who are in the audience and who are happy to answer questions via chat. So if anyone does have questions, please feel free to use the chat. Yeah, so I guess over to you, Andrew.
Thank you, Matt. And thanks for the opportunity to give this talk. I'm sorry that I'm not there with you in Cambridge. Hopefully in a year's time, everything will be normal and there will be more than 6 people in that room. And the talk I'm going to give today is about learning operators using data. And a substantial part of the talk will be about learning linear operators, although the first half will be more general than that. The work I'm going to describe is in collaboration with many other people, and I'll tell you who they are as we go along. And specifically, the work on learning linear operators is the work of Nick Nelson, who's a PhD student at Caltech. I should say, as Matt said, I welcome questions. You can either interrupt and ask me directly, or you can put them into the chat, and either Nick Nelson or Nick Kovacsky, who's another collaborator, will be happy to answer them. But I do welcome interruptions anyway. I think the talks work much better if you seek clarification when things are not clear. So and also please tell me if my voice is not clear or anything. Hopefully the sound and vision are okay. The structure of the talk is as follows. I'm going to describe the setting that I'm interested in, learning operators. Specifically for this talk, I'll look at mapping between Banach spaces of functions over a bounded domain in RD. I will discuss a little bit the topic of expressivity of these neural networks. And then I will have a short section on motivation for the discussion of the use of neural networks to learn the solution of forward problems and inverse problems. And that will serve as motivation for the analysis that we will undertake for the solution of, or the analysis of learning linear operators between Banach spaces of functions. And then I'll describe numerical results which substantiate our theory and take it beyond the confines of the theory. There is substantial work in here, not only by myself and collaborators, but by many other people. I'll try and mention many of them as we go along. The slides I will make available if Matt can put them on the website, and there's a large list of references at the end that describe work by myself and by others. Okay, so this is the setting. We're looking at a setting in which we are given 2 function spaces, which I'll call X and Y, calligraphic X and Y throughout this talk. And throughout this talk, you can think of them as real valued spaces of real valued functions over a common domain D, which is a subset of RQ. It's not necessary that they're functions over the same domain, and it's not necessary that they're just real valued. They can be vector valued, but just for to be concrete, think of this setting where X and Y are both functions over domain D, and they're just simply real valued. And we're interested in learning about a map psi dagger from X to Y on the basis of data. And the data I will refer to as pairs Xn and Yn. The Xn are in the input space calligraphic X, and they're distributed according to a measure mu. And we will suppose that the data Yn is given either exactly or approximately as the image of Xn under the map psi dagger. So the information that we have about psi dagger is through these pairs of functions, Xn and Yn. And the goal is given some operator class, which will be a parameterized set of functions from x to y, parameterized over a finite set of parameters from a subset uppercase theta in Rp, to find a value of the parameter in theta, call it theta star, at which this function from the operator class evaluated at theta star is close to psi dagger. So that's essentially the problem of supervised learning, specified to the setting in which the data pairs xn and yn are themselves functions, and in this case, functions, real valued functions over a domain D, which is, by the way, a bounded open subset, should have written that. So think of D as bounded open subset. Okay, so as you all know, supervised learning has shown a great deal of success in the information sciences, and something that many people are interested in currently is the possibility of using supervised learning for scientific applications. And I want to highlight here a couple of what I believe are the key issues in the context of scientific applications, and I'm thinking here mainly of the physical sciences. And they are the expressivity of the networks, coming up with networks which are able to universally approximate from within some classes of functions the operators that are of interest to us. And in particular then, given a network with good expressivity properties, there are two issues related to cost, and cost as a function of the error that we make in approximating psi dagger that are particularly important in scientific applications. One is the cost as measured by the number of parameters, or the overall size of the learnt mapping psi. That will have an implication for the cost of evaluating that mapping. And the second is the cost in terms of the demand on data, then the size uppercase N that of the data set needed to successfully train the model. And this talk, I'm going to focus on both of those questions. I'll describe to you recent work by a number of research groups relating to the question of cost as measured in terms of number of parameters. And I will then go on to look at cost as measured in terms of the demand on data in the setting of linear problems. And I want to say that for me, the two main applications in scientific applications, are the use of surrogate models, in which the learnt model psi is much cheaper to evaluate than, say, a complex computer code which generates psi dagger. And that enables us to undertake tasks more quickly than we might do otherwise by using the surrogate. And the other is scientific discovery, where we don't know a model, but we have data and we try and learn it directly from data. And another focus, especially in the second half of this talk, will be on distinguishing between learning forward and inverse operators. And I will return to that later. Okay, so to discuss expressivity, what I'd like to do is tell you about a number of different architectures that have been proposed for the learning of mappings between function spaces. And I'll then tell you a little bit about the theory of expressivity, universal approximation and related results for these different architectures. So the first one here I call Pca Net. Remember, there's a lot of notation to take in here. Remember that X is itself a function, and the output of this neural network is itself a function. So X is an input function, the output psi Pca is a function, and I'm here evaluating it at point Z in the domain D, because remember, I specified that the functions that we look at in this talk will be over a bounded open set D in RQ. So here at point Z, I'm evaluating the output function, X is the input, and theta are the parameters which we learn to fit to the data. And the form of Pca Net is as follows. The output function is a linear combination of psi j's, and I'll come to how the psi j's are computed in a moment, with scalar coefficients, which are a function of the input, x. L is an operator which computes a set of linear functionals of x, and theta are the parameters that are trained to get a good fit between psi Pca and psi dagger, which underlies the data. So in Pca Net, the functions psi j are computed from the data, but separately from the training of the neural network. They're computed by performing principal components analysis, which can be thought of conceptually on function space, with respect to the measure, which is the push forward of mu under psi dagger. And so principal components analysis really means computing the covariance operator of this measure and working in the eigenbasis associated with it. Lx, the set of linear functionals of the input function x, is found as the Pca coefficients under the input measure, mu. And then the alpha j's are finite dimensional neural networks, which, the family of all of the alpha j's constitute a single neural network in finite dimensions between the latent spaces identified by principal components analysis. So in this method, the output spaces are characterized directly from the data, separately from the training of the neural network. Okay. Any questions about that architecture? Because the architecture is going to become more complex as we go on.
Andrew, are you assuming that mu is known?
Well, so conceptually, mu is here thought of as known. You can think of mu as the data. This is, of course, implemented by an empirical approximation of mu given by the data. Thanks.
So, Andrew, the alpha j's, if you go back, they seem to, I guess, is just a notation, or are they really sharing weights across j's?
Yes, they are. So this is notational. So the collection of all of the alpha j's constitute the neural network, and it's trained all at once.
Okay. So,
and that notational issue will come up in the subsequent, in the next slide as well. Thank you for clarifying. Okay, so Pca Net, which has been developed by Karniadakis and co-workers on the basis of earlier work by Chen and Chen in the electrical engineering literature a couple of decades ago, and they made a deep version of what Chen and Chen proposed originally, has a form somewhat similar to what I just described, but with a number of key differences that I want to highlight. The first is that the psi j's themselves are now neural networks, and then they're not computed using Pca, they're trained as neural networks. So the parameters theta enter psi j and are trained to learn the psi j's. And in the original version of Pca Net, the linear functionals of x were pointwise evaluations at a grid of points in the domain D. Although it's very easy to generalize, and it has been implemented in versions where the linear functionals of x can be computed again using Pca coefficients as they are in Pca Net. So this is perhaps more difficult to train because of the parameters entering both, the theta parameters are entering both alpha and psi, but potentially more expressive. And you can see already from this that the potential benefit will come in settings where going outside Pca may lead to an improvement. However, what I would note about this and emphasize is that the output basis functions psi j do not depend on the input function x. Okay, so they do not depend on it. And so they are, the linear span in the output space y is once learned fixed and does not depend on the choice of input. All right, so now I'd like to describe something I'll just call Paramet. And let me just explain where this perspective comes from. So the previous two methods I described viewed the operator that we're trying to train as being a function from x to y. But remembering that y is itself a space of functions over a domain D, which are real valued, you can also take the viewpoint of learning the function from x cross D to R, as a neural network. If you take that perspective, you come up with a network architecture that has the form that you see here. And I'm making the assumption that the last layer of the neural network is linear, so that the last layer learns these weights b to j. And then the basis functions in this setting depend jointly on the input, which is a set of linear functionals computed from the input function x, and the point z in the domain D. Now, something that's worth noting here is that Pca is a special case of Paramet, in which the psi-j's are separation of variables, essentially, in which the psi-j's are written as a product of functions of the linear functionals of x and functions of z. And so as a consequence, some of the results that are used to understand the universal approximation properties of Pca apply directly to this Paramet. So this is potentially more expressive, but harder to train. So if you look at the three methods I've described so far, they become progressively harder to train, but have advantages as a result of that property. Okay, and then finally, I would, no, not finally, fourthly, I'd like to mention the Fourier neural operator. So this is part of a wider class of operators, kernel-based. And let me just take you through this written in a form where it can be directly implemented using pseudo-spectral methods. So the Fourier neural operator has three components that are combined together. The first are the operators r theta and q theta. These are just finite dimensional neural networks applied pointwise to functions varying over z in the domain D. D, remember, being a subset of RQ. So r theta and q theta are standard finite dimensional neural networks applied pointwise at every point z in the domain. Second thing is P, which is the pseudospectral projection onto trigonometric polynomials. And then thirdly, we have these operators L made from P, and they have the form of the standard component of a deep neural network, namely composition of pointwise activation function with an affine transformation. What makes this special and particular to function space operations is that the affine transformation involves the kernel K, which for this particular Fourier neural operator is a convolutional integral operator and is therefore evaluable quickly using the FFT, or specifically the DFT, when implemented in finite dimensional setting. So this method, which is joint work with a large group of people from Caltech, highlighted here, has shown great success, and I'll come to it and how it compares with Pca, both of which are comparable, I think, in behavior. Finally, I just wanted to mention a fifth architecture, which is the random features method. This was developed by Nick Nelson, whose work I'll also be describing later in the talk when discussing learning of linear operators. But random feature methods, on the face of it, maybe look a little bit naive, but I want to tell you why I think they are an important component of scientific machine learning with a lot of promise. The form that they have is...
Andrew.
Yes, please.
Sorry, I have a question about the previous slide. Now, this sigma that you have there, do I understand it correctly that it still acts in infinite dimensions?
It acts in infinite dimensions, but pointwise. So it's what would be called an Emitsky operator. So sigma is a function from R to R, but you lift it to a function acting on, to an operator acting on functions by pointwise evaluation. Okay, so you assume that the spaces where you lift it to that mid pointwise evaluations. So yes, that's right, exactly.
Thanks.
Thank you. Or pointwise evaluation almost everywhere is sufficient. Okay. Thank you for that question. Okay, so in the random feature method, the form of the architecture is very straightforward. It's a linear combination of a fixed set of functions psi. The functions psi are random. They take as input some linear functionals of x, the input function, and they're parameterized by a random parameter gamma j, which in the standard version of this method, gamma j's are chosen IID from some probability measure. So together, the collection of these psi's is just a collection of random functions which have not seen the data. And then one simply optimizes over the coefficients theta j. So what the advantage of this is that the optimization is simply a quadratic optimization, and you can easily append it with other things such as sparsity or other constraints that you might wish to. But from a training point of view, this is very straightforward. The disadvantage is the fact that the psi's have not seen the data. However, there is the possibility of implementing this method hierarchically in a manner such that the basis functions do see the data. And in that context, I want to mention that the random feature methods can be viewed as a Monte Carlo approximation of Gaussian process or reproducing kernel Hilbert space methods. Those methods are well known to, in the case of Gaussian processes, to benefit from a hierarchical perspective in which the basis functions are trained to fit the data. And you see that in the book of Rasmussen and Williams, for example. And recent work of Hooman Awadi, who is my colleague at Caltech, has shown the possibility of more generally looking at kernel methods in very high dimensional problems and training the kernels to see the data. So I think there are a lot of possibilities for making random feature methods more expressive in terms of training the basis functions to see the data, and yet retain the advantage of the quadratic optimization over the weights theta. So I have a lot of faith in this methodology as being something which will perhaps grow in importance as time evolves. So let me say a little bit about all of these from the perspective of universal approximation and highlight some of the theory, some of it coming out of my collaborators and others that I'll highlight here coming from George Karniadakis and Sid Misher and Sam Landhaler at ETH. So for the three methods, Pca, Pca Net, and the Fourier neural operator, there are universal approximation theorems. I'm just stating them loosely here. You can follow up the references if you want the details, but I want to highlight some of the differences and the nature of the theorems. So for the Pca method, firstly, I'm expressing the first two here in terms of Bochner norm. So this is the L2 norm of mappings between spaces X and Y, weighted by measure mu on the input space. And the Pca universal approximation theorem is in a form in which we average the Bochner norm squared over the data. The reason for that form of the theorem is because most natural control over the principal components analysis part of the theory, and in particular, approximation of principal components analysis with finite amount of data, leads to results which are most easily expressed by averaging over the data. But you can also derive results in high probability of the same type. This work, paper 10 of Sam Landhaler, Sid Misher, and George Karniadakis, looks at Pca Net from the perspective of universal approximation in the Bochner norm, and shows that there is a universal approximation theorem in that sense. And work of Nick Kavatsky, who is a student at Caltech, also with Sam and Sid, performs a similar analysis for the Fourier neural operator. Their results are stated as supremum over input functions from a compact set, but they are also easily can also be derived in this form here that the Pca Net results are presented using the Bochner integration. So, these really showing that there's a lot of expressivity in universal approximation theorems. There is, however, the question that I highlighted at the beginning of the cost of these methods, and whether or not they successfully beat the curse of dimensionality. What the work of Lanthaler, Mishra, together with Karnidakis and Kavatsky show is that for DeepONet and the Fourier neural operator, it is possible to beat the curse of dimensionality. And I should mention also that earlier work of Chris Schwab and Zek, which shows similar results on specific problems. So these show that both these methods have great promise from the perspective of the size of the neural networks and therefore their cost to evaluate and their competitiveness from the point of view of accelerating scientific computations using surrogate modeling. The PCA result has not been extended to demonstrate beating the curse of dimensionality, but we believe it should be able to be extended. I also want to mention that I said earlier that DeepONet is a special case of what I called Paramet. As many of you will know, these universal approximation theorems have come with no guarantees about the neural networks that you actually find in training. They are simply existence results that say there is a neural network with a given property. Therefore, since DeepONet is a special case of the Paramet, it follows that everything stated about universal approximation for DeepONet also holds for Paramet. For random feature methods, the theory is open, but I think begging to be developed for the reasons that I've described to you. And I also want to mention recent work of Korolev, who is a postdoc at Cambridge, who studies two-layer neural networks on Banach spaces. Okay, so this work goes some way towards showing that from the perspective of cost per unit error, where cost is described in terms of the size of the neural network, the methods that are being developed in the literature show considerable promise. And now I want to push towards discussing cost in terms of the data hunger or the amount of data required for successful training. And in particular, in doing that, I want to look at the question of learning forward problems versus inverse problems. So perhaps I should just pause and ask if there are any questions, because I'm shifting to a slightly different topic now, moving to cost as a function of data, as opposed to cost as described by the amount of data required, rather than cost as described by the number of parameters used. Those are rather different issues. Yes, Philip.
What do you mean in this context by overcoming the curse of dimensionality?
Thank you. I should have said that.
Beating.
Yes, so the question that is being addressed in the papers of Lanthaler, Mishra, and Karnidakis, or Lanthaler, Mishra, and Kavatsky, with regard to curse of dimensionality is this: if I want to achieve a given error of size epsilon, we ask the question, how many parameters, and that can be measured in different ways. That can be the depth, the width, etc., of the neural network. So let me just couch it in general terms of the overall number of parameters. How does the number of parameters used to describe the neural network grow with epsilon? And that's important for the scientific applications that I mentioned, especially surrogate modeling, because if the curse of dimensionality shows up, then the neural networks that are trained may have so many parameters that they're expensive to evaluate. So the question is, how do the cost in terms of number of parameters scale with epsilon? And roughly speaking, the beating the curse of dimensionality refers to obtaining polynomial behavior in epsilon with respect to the number of parameters required. And I should say that the nature of the results for both DeepONet and FONet in this context are of the following type. There are, in general, examples where the curse of dimensionality will show up in that the scaling with epsilon is way worse than polynomial, so exponentially bad in epsilon, or 1 over epsilon. What Lanthaler, Mishra, Karnidakis, Kavatsky show in various cases is that for specific problems, and this builds actually on the earlier work of Schwab and Zek, for specific problems using the specific structure of the problem, the number of parameters will grow polynomially with epsilon.
All right, thanks.
Thank you, Philip. Thanks for that clarification. Good question. Okay, so that I'm now going to look at the cost. So in some sense, the number of parameters, it's relevant to training, but it's specifically very relevant to using the trained neural network as a surrogate, because it has implications for the cost of running the model once you've trained it. The cost I'm now going to turn my attention to is how much data is needed to train to a given level of accuracy. That's a different question, but super important for lots of scientific applications where we may not have as much data available to us as in the standard machine learning applications, such as image classification. So with that in mind, let's push towards understanding how much we need in terms of data to get a given level of accuracy. And also we'll do that in the context of discussing both forward and inverse problems. So let me start by discussing a forward and an inverse problem, and I'll show you some results from the forward and comment on some results from the inverse. So this is a simple linear elliptic partial differential equation, Dirichlet boundary conditions. It's the Darcy flow that many of you will be familiar with. Models flow in a porous medium. So this is just mass conservation, F are the sources and sinks of fluid, and there's a specific constitutive model that's being used to describe the velocity field as a function of the pressure U, which is that the velocity field is proportional to the gradient of the pressure U, and the constant of proportionality here is a function, A of Z. It could indeed be a tensor, but in this case, we'll look at it as a function. So the forward problem here is given, let's think of the sources and sinks as fixed for the moment. Given the forward problem is given A to the coefficient of this equation to find the solution U. So one is interested in the parametric dependence of the partial differential equation. And I'll show you results in a moment, which just compute the relative error as defined here, averaged over the training data. Of course, this is computed empirically. And I've done it in a relative sense. So we look at the error of psi dagger, which is the truth underlying the data, to the trained model in L2 over the domain D, scaled by the norm of the true solution. One could also look at learning the inverse map. So we're going to be given data which is in the form of pairs of A's and U's. You could imagine doing this with the same training data to try and learn the inverse map from U to A. I just wanted to comment a little bit on this inverse problem. Specific inverse problem is studied by Richter in this 1981 paper, who proves uniqueness and stability of the inverse problem, but weak stability. And formulated as Bayesian inverse problem in this paper with Masume Dashti. And the very recent interesting work of Richard Nicol, who's at Cambridge, and his colleague Pca Net, also at Cambridge, which studies this inverse problem and others from the perspective of information theory. You'll find that on the archive. So this problem, the way we have been solving it numerically, is concerned with random functions in which actually binary, with take two known values with ratio 4, but with random interfaces and mapping. So that's a typical input. This is a typical output. And we have a probability measure on such inputs. The random interfaces are computed as level sets of a Gaussian random field. And we learn the mapping from the inputs of this type to outputs of the type on the right, the pressure. And this data shows two things. So firstly, just focus on the red curve for the moment. I'll distinguish between the green, blue, and red in a second. What this shows is that the relative test error, which is on the vertical axis, is around 3%. And the first photo, and also we get the same level of relative test error at different levels of resolution. That reflects the fact that the architecture is designed on function space, And so provided you're resolved enough, you get the same answer at all levels of resolution. And the residual error of 3% describes, is an artifact of the finite data set used to train this problem. So if you like, 3% here is quantifying, given the fixed amount of data we have here, it quantifies the residual error from the training. Now, the three different colors, green, blue, and red, corresponding to integers d equal 20, 50, and 70, they correspond to the number of linear functionals of the input function, which are used in training the neural network. So if I just go way back to Pca Net, this is using Pca Net. The input to the neural networks in the form of linear functionals of the input function x, and those linear functionals are Pca coefficients with respect to the input measure mu. So what you're seeing in this figure, if you compare the green, the blue, and the red, is the effect of taking more and more linear functionals to capture the input function. And as many of you will know, the theory of probability measures on Banach space is developed precisely by looking at the dual space, the set of linear functionals on the Banach space, and characterizing the measure through them. And so it's unsurprising that we should be able to characterize with greater and greater accuracy the mapping in question, measured in an average sense with respect to the input measure mu. It's unsurprising that as we take more and more linear functionals, we should be able to capture it accurately. Okay, so there's a lot of stuff in here. There's the effect of the linear functionals, that's the different colors. There's the effect of resolution, that's because the method is defined on function space. And then there's the size of the error, which is small, but remains 3% at all levels of resolution because the amount of data that's used is finite. But what you see from this is a success story in training the forward map, namely that we are able to get the relative test error to be small, based on, in this case, I can't remember, but I think on the order of 100,000 data points. Nick Kovacsky, if you're here, you can type in the chat exactly how many data points we used. It could have been millions, but I think Nick will know. The point is, this was a tractable problem. On the other hand, the inverse map, which I don't have data to show you, but learning the inverse map from the same data results in errors which are much larger on the order of 10 or 20%. So the question I want to get to now is the question of how much data is needed to train a neural network, and how does the difference between forward, that is well-posed problems, and inverse, that is ill-posed problems, how does that show up? Okay, so before I go on to that topic, I just want to say a few things generally about machine learning for inverse problems, and to highlight the fact that there are three ways that I'm aware of, three primary ways in which machine learning might be usefully used in the solution of inverse problems. And the first one relates to the fact that, especially if you're interested in Bayesian inversion, solution of the Bayesian inverse problem requires numerous evaluations of the forward map. So if you can find a surrogate forward map which is cheap to evaluate, and neural networks provide one possibility for doing that, then that enables the possibility of accelerating the inversion process by using a faster forward map. And in this paper, Nick Kovacsky and Zhongyi Li showed that for inverse problems with the Navier-Stokes equation and Fourier neural operator, which was exhibiting in the regime studied in that paper, a speed up of order 1,000. Therefore, one was able to solve inverse problems for the Navier-Stokes equation that would have been intractable without the use of the surrogate model to replace the forward map. So that's one approach. Second approach, which has been developed on a number of different fronts, is to use data to learn regularizer, rather than postulating a regularizer as a Tikhonov or Tikhonov-Phillips regularization, rather to actually take data and use it to learn regularizer. And I would like to draw your attention to this review article of Simon, Carola, and others, and also to a beautiful paper of Sohan Chandrasekaran in Foundations of Computational Math, which take the second perspective. The third one, which I'm going to talk about in the remainder of the talk, is actually learning the inverse map directly from the data. And this is something which was undertaken at the discrete level in a recent paper of Matti Lassas, Wong, and Martin de Hoop. And we're going to study it here without discretization, the level of function space. Okay, so I think all of these approaches are important and interesting, but just to highlight that the remainder of the talk will be about the third, learning the inverse map, and comparing it in terms of how much data is needed with learning the forward map. Okay, so to do this, we're taking first steps into this problem. We're going to look entirely at learning linear operators. So this work is, as I said earlier, is from the PhD thesis of Nick Nelson. And the paper is recently on the archive, you can see it here, and is joined also with Martin, Nick Kavatsky, who I've mentioned earlier. And the main focus of what I'm going to describe is on measuring the cost in terms of the amount of data required per unit error in the approximation of the operator, here linear, from data. Okay, so let me take you through this, and first of all give you the setting. I'm going to formulate the learning of a linear operator in two ways, one from the perspective of statistical learning, and secondly, from the perspective of Bayesian inversion. And then I will link those two different approaches, and using the theory of Bayesian posterior consistency, get error estimates for the learning of L, the linear operator, and those error estimates will quantify the hardness of the problem in terms of how much data is required for a given level of accuracy. All right, so that's the key question, is comparing the hardness of learning different operators. So here's the setting. X and Y I will take to be the same Hilbert space with inner product and norm as shown. The objective is to learn L dagger, which maps from possibly densely defined, maybe densely defined, maps from the domain of L dagger, which is a subset of H, into H. I'm going to introduce a measure pi on X and Y, joint measure. So X and Y, again, these are function spaces. So capital pi is a measure that will be constructed as follows. So given L dagger and given X distributed according to mu, which is a Gaussian with covariance C1, and given eta, which is a white noise, I'll come back to the white in a second, and given the assumption that X and eta are orthogonal, or independent random variables on H, well, eta is not actually supported on H, but supported on a larger space which contains H. Given those assumptions, and given that Y is related to X and eta through this affine transformation, that defines a probability measure on X and Y, which I call uppercase pi. Just to comment on the fact that eta is here white is not necessary. You can start with a more general probability measure on Gaussian probability measure on eta, and then whiten the problem to obtain the problem as I will analyze it here. So it's not a restriction of the theory, it's for simplicity of presentation. So we're given n, uppercase n, draws of pairs of functions x and y from probability measure pi, and we're interested in learning L dagger. And to contrast forward and inverse problems, I'm going to fix x and y and learning the map from x to y, and forward and inverse problems will be distinguished by whether or not the operator L dagger is compact or unbounded. Okay, so the results will differ depending on the compactness or unboundedness of L dagger.
Andrew,
Any kind of questions about the setting?
very big question. So the assumption that the prior is Gaussian also, is that because you need later on theoretical convergence results or something? Why do you, because that seems a bit more.
Yeah, that could be relaxed actually. So I'll come to the structure of it's a very sharp question. I'll come to the structure of the inverse problem in a moment. It's not really crucial that X is Gaussian. It's because indeed, if I fix it, let me discuss that when I get there. But we can indeed relax X being Gaussian, but crucial that eta is Gaussian. And given that structure, I will use some conjugacy of Gaussian measures that stem from eta, but not from X. Thank you.
Can I also ask a quick question? I might be missing something, but if you think of this L dagger as the inverse, as the unbounded inverse, then what role does the noise eta play? It cannot be interpreted as measurement noise anymore, because X will be the images and all the data, and Y will be the.
That's correct. I will only say that this is our first step into this, trying to answer this question, and I think I would like to think of the eta as quantifying inexactness in the data that we're collecting. But I would not claim that the specific statistical model that we analyze would adequately represent that. It would just give some sense of the stability with respect to perturbation. But the question you ask is absolutely spot on. So we've done what we've done. I think it says something about the question, but what studying a better model for the noise inside the acquisition of data would be beneficial on top of what we've done here. Thank you. Okay, so let me first formulate this problem from a statistical learning perspective. There's a couple of things that stem from the infinite dimensional perspective in the form of the risk that I want to highlight. So the risk may not look familiar as written at the moment, but I'll explain why it's written like this in a second. So the risk and the empirical risk are defined here in this manner. So the risk itself is averaged over the probability measure pi on the pairs X and Y. And the empirical risk is the empirical approximation of that expression together with a regularization of the operator L, which is in a Hilbert-Schmidt norm, and then we're weighting L by W1 and W2. You don't need to worry too much about the W1 and W2. How they play out, I will show you explicitly when we get a bit further into the analysis. What I would like you to pick up from this slide is why the risk looks this way. You notice if I add minus a half y squared to the risk, then I'll get something which is a more familiar expression of the risk. So this contribution here. The reason for the subtraction of the half y squared is because it's almost surely infinite. So this quantity makes sense in the infinite dimensional setting precisely because we've essentially subtracting two infinities here. So I'm happy to discuss this in more detail with anyone who's interested afterwards, but this is a problem that many of you will be familiar with from Gaussian measures on Banach space. Also, I wanted to highlight earlier work on looking at learning operators from the perspective of statistical learning in this paper of Tavaggi, De Hoop, and Dominic. All right, so this is a formulation, and want to be completely clear about what we're assuming. So it's a very straightforward, simple setting in which everything is simultaneously diagonalizable. I will show you that the results that we obtain by making this assumption appear to lead to theory which is valid outside of the the assumptions made here. So these are very strong assumptions, and I recognize that. We're going to assume that we have a known orthonormal basis for H, and the hypothesis space for learning L is going to be operators which are diagonal in that orthonormal basis. Right, so they're written in this way as an infinite sum of outer products of the orthonormal basis with itself. And then we can define, and then the coefficient sequence Lj will become our unknown, and that will just be viewed as an element of the sequence space Hs, which is the little L2 sequence weighted by j to the 2s in the summand. And then the domain of L follows naturally from this diagonalization of L. And L dagger, with this definition, L dagger, the truth, is the minimum of the risk over this hypothesis space, assuming that L dagger is in that space. And L bar n, which I will highlight here in red, is what is the minimizer of the regularized empirical risk, which is what we actually have access to, and therefore L bar n is what we can compute. And it will also be of interest to us to look at the excess risk and the generalization gap, which is standard concepts in statistical learning theory, averaged, so averaged over the data. So the excess risk comes from looking at the risk itself evaluated at the truth and evaluated at the minimizer of the empirical risk. And this is equal in this setting to the average of the Bochner norm squared of the difference between the minimizer of the empirical risk in red and the truth. Okay, so the excess risk relates directly to an error estimate comparing the truth with what we can estimate from data. And then the generalization gap is also relevant because it involves a computable quantity, which can then, by adding the excess risk and generalization gap, can be used to estimate what you need to generalize, what's needed to generalize.
Can I ask another quick question, please?
Yes, please.
So this excess risk, which measures the difference between the learned L dagger and the true L dagger in the Bochner L2 norm, this is different from the operator norm, right? Because L dagger may be unbounded.
Absolutely, yes.
The operator norm, but
thank you very much. Very, very crucial here is working with the Bochner norm. And the reason is that we will choose the measure mu. So where is that? Here's the measure mu. So that this is supported, so that it's supported on the domain of L dagger. And indeed, the operator norm may be unbounded, but the Bochner norm we think is the right measure for this because it enables us to look at the application of the unbounded operator.
Thank you.
Thanks. Okay, so let me now reformulate the problem in terms of Bayesian inversion. So here we have the linear inverse problem. This is the set of data that's available to us, n copies of this problem. Then if you concatenate all of this, I want to highlight the fact that, of course, L is a linear operator, so we think of L acting linearly on Xn, but the collection of all of those objects can be viewed as a linear operator, K sub X, acting on the linear operator L. So K sub X is defined through pointwise evaluation of L on the data set Xn, with n ranging from 1 up to uppercase n. So if you then concatenate all the data, you can write it like this. And then following on from the question a few moments ago, just for the moment, think of fixing X. E is white noise. This is a simple, since if we place a Gaussian prie on L, and since E is itself Gaussian, for fixed X, this is just a conjugate Bayesian inverse problem in which the posterior distribution on L is also Gaussian. And that's for fixed X, and then one can then look at that distribution over X varying. We have chosen to look at X itself as being Gaussian, but as discussed earlier, other possible choices for X un-Gaussian could also be made. So then this is just summarizing what I've just said. So if we put a Gaussian prior on L, everything diagonalizes, and you basically have an infinite set of scalar linear inverse problems, which characterize, therefore, the coefficients lowercase script LJ, which the sequence which characterizes the operator L in our hypothesis class. So there are a number of exponents knocking around here that I want to draw your attention to. Alpha 1 is an exponent that characterizes the regularity of the input space X, and alpha 3 is an exponent that characterizes the regularity of the prior measure on operator L. And we've scaled everything so that eta is Gaussian. So there's earlier work which looks at this inverse problem from the perspective of learning X when L is known from Y. And this work from in Annals of Statistics by Napick, van der Vaart, and van Zanten underlies all of our analysis. So the techniques that they developed, we exploit, although the problem is slightly different. We are able to make a great deal of use of their work from 10 years ago. I should say that their work also is in the simultaneously diagonalizable setting. There is work here with Sergio Sagapio and Stig Larsson, which goes beyond the diagonal setting and could be applied to look at our problem from that perspective as well, beyond the diagonal setting. Okay, so the posterior then is a Gaussian. The mean of the Gaussian is L bar n, here in red, which is the minimizer of the regularized empirical risk. W1 and W2 are chosen to affect this particular outcome as being the prior on the weights Lj, the operator that we learn. And this Bayesian inverse problem can be factorized into an infinite set of scalar Bayesian inverse problems. All right, so then leveraging the theory of Napick, van der Vaart, and van Zanten, you can prove the following theorems. That there are a lot of exponents in here. Alpha 1 and alpha 3 I've just described to you. Alpha 1 describes the regularity of the data. Alpha 3, the regularity of the prior measure on the sequence Lj, which characterizes the operator L dagger that we're trying to learn. And then there's the regularity of L dagger, the truth, which is in the sequence space HS, which is the J to the 2s weighted in the inner product, little L2 norm. So these things are notoriously hard to take in terms of the behavior with respect to the exponents. So let me just say that in finite dimensions, without the issues of infinite dimensionality, one would expect order n to the -1 for this first theorem here, and order n to the -1/2 for the second theorem here. The roles of the exponents alpha 1 and alpha 3 are to demonstrate settings in which genuinely infinite dimensional phenomena occur, and the rates as a result are less than n to the -1 and n to the -1/2 in these two different theorems. So the first theorem concerns the error. You can view this in a number of different ways, but one is that it gives posterior consistency in a Bayesian sense, excuse me, by computing the error between L under the posterior distribution, that should be an uppercase pi there, and the truth, measured in the Bochner norm, and then averaged over the data. That is the standard thing that gives you Bayesian posterior consistency as commonly stated in the statistics literature, in this specialized to the Gaussian setting. And it coincides with estimating the excess risk, as I showed you on a previous slide. And we get given rate of convergence here. I'm sorry, I realize I should have finished 2 minutes ago, and I will finish in 2 minutes. I apologize for running over, I lost track. And the generalization gap, one can use similar analysis to get an estimate of the generalization gap. We can get lower bounds in many cases with matching rates, The results here described are an expectation, but we can get them also high probability with respect to the xn's. And we can compute extensions to test measures where the Bochner norm is not measured with respect to mu, but with respect to another measure, mu prime, if you think that's a form of generalization. Now, just to cut to the chase, here I'm comparing compact, bounded, and unbounded operators. Compact in red, bounded in blue, unbounded in black, looking at the rate of convergence as a function of the amount of data on a log scale, rate of convergence. So this is a log scale, so the slope gives you the exponent. And what this picture shows on a specific example is that the learning a compact operator is easier than learning an unbounded operator. The theory is sharp. This figure shows a comparison between the exponents that we compute over a range of alpha 1 and alpha 3 in both the experiment and theory, and they coincide. And finally, we've also done experiments which go beyond the confines of our theory to a setting in which L dagger is not diagonalizable. So we learn a full matrix. And the key point here is that we get the same result. Numerically, you see this ordering, which compares the learning of compact, bounded, and unbounded operators and shows that the unbounded operator learning is harder. All right, thank you. That's my conclusions. I have lots of references here, and if anyone would like the slides, I will make them available to Matt, or you can contact me directly. I'll just leave the conclusions there and apologize for running over by 3 minutes. Thank you.